have lov til at byde jer velkommen til vores generalforsamling. Og vi starter med et foredrag først. Og i år er det Mostrom, og nu kender det selv, ved jeg ikke. Men du holder et meget spændende oplæg, tror vi nok. Massebalancen på Grønland. Det er jo noget, som I arbejder med ved DMI, og det er der også arbejder med på DTU og på KU. Det er noget, der interesserer mange. Jeg kan se, at der er ikke kommet så mange udefra, men altså fra for eksempel DTU og KU. Der er mange af vores egne, og det er dejligt. Så, måske kommer der nogen efter dit foredrag til generalforsamlingen. Det tror jeg nok ikke, men jeg har bestilt plads på en restaurant, der hedder Vincent. Der har vi også været for et par år siden. Til 15 mennesker, men der er plads til flere. Jeg vil godt tænke mig lige at spørge her, for så vil jeg ringe til restauranten og sige, hvor mange vi cirka kommer. Hvor mange har lyst til at komme med og spise bagefter? Ja, det ligger, man kan tage S-toget fra herhen til Svanemøllen, og så er det lige ved siden af Svanemøllen på Landskronagade. Bilen er et problem. Jeg vil foreslå, at du tager S-toget derned, og så tager S-toget tilbage igen og henter en bil. Det kan ikke betale til bil i byen.
Svanemøllehallen, der kan man parkere lige overfor.
Og jeg tager telt. Vil det passe? Ja. Men til cirka 15. Vi siger til, at vi kommer 18, så er der nok plads. Er du med ud at spise bagefter?
Ja, jeg skal ringe til familien og tjekke den på.
Ja. Så stiller selv, så er der jo lige plads. Men jeg regner med, at det tager en times tid, eller sådan noget, eller kan du se?
Ja, 3 kvarter.
Det vil være meget fint. Jamen, værsgo.
Tak skal du have. Så jeg hedder Ulf Morten. Jeg har boet her i Danmark i næsten 7 år faktisk, så det er lang tid nu. Og jeg har lige haft min 5-års jubilæum på DMI. Jeg har været på det sidste uge, så det er rigtig godt. Men jeg skal gøre denne foredrag på engelsk. Jeg undskylder mig, jeg kan tale lidt dansk, men jeg snakker det ikke så godt, når det er teknisk. So I should say as well, I have to say that this research I'm presenting has been sponsored very generously under these projects by the European Union and Danish FLU and the Nordic Council of Ministers. So lots of people paying for interesting research on the Greenland ice sheet. I know that most people here are meteorologists or interested in meteorology. Who's been to Greenland? I know you've been to Greenland, John. Anybody else? Yes, quite a few people have been to Greenland. Yes, lots of people. Great, excellent. Anybody working on Greenland? Yes, I know you're working on Greenland. Anybody else? Okay, so I hope I'm not going to get too technical. If I get too technical, or if you have any questions, just ask. I don't mind being interrupted in the least. And also, I'm told I talk quite fast in English, which is reasonable because I am English. So if I do go too fast, just tell me to slow down and I won't be offended at all. I started out as a glaciologist actually. Now I run climate models, but this is a picture of my field site. Once upon a time I used to go into the field. My PhD was on crevasses and carving glaciers. And this is a picture of my PhD supervisor for scale, so you can get an idea of how big some of these glaciers are. This is actually a relatively small glacier in Iceland. It's nice and accessible, which has some big advantages. And I mentioned it because I think there may be a bit of confusion about 2 terms I'm going to use a lot. On the websites, on the DMI website, they said I was talking about total mass balance. And I thought I was talking about surface mass balance, so I'm going to be quite careful and define the two. My PhD was actually quite closely related to one element of the total mass balance. That is the dynamic component. And the dynamic component is basically this. It's carving, and this is Breidamørkjökull in the summer. You can see these big icebergs just falling off the front. The other part of the dynamic component is melt, and that happens basically underneath these floating bits of the ice. They're very important parts of the mass loss component. Between 30 and 50% of the total mass that's lost from Greenland is dynamic. It's quite dangerous. This happened on my PhD. This was about 3 days after I fell down a crevasse, which probably explains why nobody's done it since. or before actually. The bonuses, I got great data from my field sites, and those papers get cited a lot because nobody else has data from crevasses like we managed to catch. So these days I tend to sit mostly behind a computer. It's a lot less interesting in some ways. So I'm mostly going to talk about surface mass balance, which is what I work on now here at DMI. And it's the other component of the mass budget. And very simply, we'll get more complicated, but very simply, snowfall falls on glaciers. Here we are digging a hole, a snow pit, to measure how much snow has fallen on the glacier. This is in Svalbard. I've done a lot of fieldwork in Iceland and Svalbard. I haven't actually done that much fieldwork in Greenland, so there won't be very many Greenland pictures here, I'm afraid. So snowfall falls on the glaciers. This is the positive term in our mass balance equation. And then it melts and the water runs off, and this is meltwater pouring down the Mulan on Brødremarkukel again, and that is the negative term of our surface mass balance equation. This, I hope, is very clear. So, why do we care about mass balance? It's kind of obvious. Snow falls in the winter and it melts in the summer, and why does anybody care about it? Well, people didn't really care about it very much until the early 2000s, actually. And then this started happening. This is 2005, and you can see the pale pink is the 1992 melt extent. It was a fairly typical year, 1992, for the mid-90s. And then in the early 2000s, we started seeing really big melt extents across the Greenland ice sheet. People went, that looks like a problem. And I apologise, I can't remember the reference to this graph, but basically some scientists went out and measured stuff around the Greenland ice sheet and said, is this unusual? And you can see here we have a melt extent index, which is based on some marine proxy. And the sharp-eyed amongst you will notice that in the sort of 30s and 40s we had quite a lot of melting, then it got cooler again, we got less melting, all the way through the 80s and 90s, and then it's come back up again. And this graph stops in 2010. So 2012 was kind of off the scale. So that's kind of interesting. Now this is from the most recent IPCC report. Does everybody know what the IPCC is? Good. It often surprises me how few people know what the IPCC is actually. So this is from the most recent report, and this is from chapter 5, I think, the cryosphere anyway. And it just shows sea level rise since 1992 and where we think the water has come from. You can see at the moment, the glaciers, this is only the small glaciers and ice caps around the world, the Alps, Norway, Iceland, the Himalayas, South America, Alaska. They're actually contributing most from the cryosphere at the moment. But these glaciers are really small, and give them 20 years, that contribution will be outpaced, probably, we think, from the ice sheets. And you can see that Greenland is currently outpacing Antarctica, we think, in terms of the sea level equivalent rise from, this is from both surface mass balance and calving loss. And then just to clarify, this is Greenland alone. You can see we've seen this very dramatic increase in the early 2000s, all the way up to about 8 millimetres sea level equivalent. So, currently, we estimate Greenland is adding about 0.6 millimetres per year to global sea level rise, global mean sea level. I will come back to that in a moment. Does everybody know what the RCP scenarios are? Who has not heard of the RCP? It's okay, it doesn't matter, I'm going to explain what it is. So, RCP stands for Representative Concentration Pathway. It's not very sexy. Basically, it's a way of determining how many emissions are going, or how much greenhouse gas emissions are going to contribute to the warming of the planet by the end of the century. And the number reflects a kind of energy input at the surface of the Earth. So it doesn't really matter how we get there in the way that RCPs are calculated. It's just if we keep emitting at this rate, we will hit this pathway. This mass of lines is very, very complicated, so I'm only going to point out a few. This one, RCP3, is staggeringly optimistic. It assumes that by 2020, not only have we stopped emitting greenhouse gases, we will also start to remove them from the atmosphere. And by the end of the century, our CO2 will be down to close to pre-industrial levels. This is the RCP 4.5, this orange line, and most model simulations that we use in climate modelling and ice sheet modelling actually use this 4.5 scenario, which is a very middle-of-the-road scenario. This red one, RCP 8.5, kind of goes off the scale a bit. It's a bit frightening. This black dotted line is actually our current emissions. So this is where we are at the moment, just a little bit above RCP 8.5. I think more people should know about this graph. That's why I'm presenting it here. So these then show, also from the IPCC report that was published in September, what we think is going to happen to sea level in the next century. And there are huge uncertainties on all of these graphs. And these are different scenarios. So we have 2.6, which is something like this blue one here. 4.5, which is the middle scenario, which is the everybody hoping for the best scenario. And 8.5, which is the one we're closest to right now. But I should say that we won't really know until sort of middle of the century which one of these we're actually on. And you can see that if we take the sun, so the little green line, which is very faint, I apologise about that, is Greenland ice sheet. And you can see the 8.5 has us getting close to a metre, 4.5 has us at the worst end, but more likely around about 0.7 by the end of the century. But there are huge uncertainties, and we don't know how quickly this is going to happen, if it's going to happen, what will the response of the ice sheets be to these kind of emission scenarios. So that's why everybody is interested in the Greenland ice sheet, or they should be. Furthermore, sea level rise will not be globally uniform. So I just showed you global mean sea level, and it really matters where the water comes from, for very interesting reasons related to gravity, pressure, and yeah, that's mostly the most important reasons. And then a local rebound of the land masses as well is important. If Greenland melts, and only Greenland melts, and we get no melt at all from Antarctica, so these are model experiments, sea level around sort of the northern UK, Norway, northern Denmark may actually go down, because we don't have this big ice mass sitting here pulling water towards the northern hemisphere anymore, basically, and then you get this rebound effect, the land rises because the ice is gone. But if Antarctica melts and Greenland doesn't, not very likely, but let's just say in the model world, Antarctica melts, Greenland doesn't, suddenly we get all the water, also the Central Pacific, but the northern hemisphere sees Antarctic ice melt rise. Now, so this is why it's very important to find out which of the ice sheets are melting, how much they're melting, and where is the water going to. So, mass budget. Has anybody seen a diagram like this before? Yes? Quite a lot of people have seen this diagram before. Very good. I hope this isn't going to be too simple for you. So, this is how a glacier grows. We get little snowflakes falling, and they accumulate and they compress and they become ice. The ice flows. It flows out to the sides where it forms icebergs, floats in the river, in the sea. In other places, it gets low down, the glacier gets, the snow falls and falls, and then at this point here, it's quite low altitude, it melts, the meltwater runs off, and goes into the ocean eventually. We have some other processes we need to think about. Sublimation, the evaporation from the surface. We need to think about refreezing of meltwater in the snowpack, because not always, the meltwater doesn't always run off straight away. And we have to think about ocean circulation, because it turns out that these glaciers are quite vulnerable to warming oceans, and if you get warm water coming in here, you can trigger quite large-scale retreats, and we saw this in Greenland in the early 2000s. So, our surface mass budget, or surface mass balance, the two terms are interchangeable basically, plus our dynamic budget, so icebergs and melt, gives a total mass budget. And our surface mass budget is accumulation from snowfall and ablation, melt, basically. And we can calculate accumulation based on snowfall, condensation, refreezing at the surface, refreezing of meltwater, and ablation is a combination of melt and sublimation. I hope that's clear. Very simple, really. So how do we measure this in Greenland? And there are lots of different ways to do it, and they come up with different estimates, which is why these sea level rise charts I just showed you have quite big uncertainties. One of the obvious things to do is run a regional climate model, and that sort of shows mass change. These all show mass change for the period, I think this is 1990 to 2010, this one. And these ones are 2003 to 2012, 2003 to 2006, and 2006 to 2012. So they are different periods, but I'll come back to that. We can measure the surface change using radar and laser measurements, and this is IceSat measurements, just shows surface lowering. And this one is the same thing using radar measurements. And you can see that we have an increase in the centre and then a lowering around the margins, which is sort of what you'd expect with enhanced melt. GRACE has kind of been a bit of a game changer. Has anybody heard of GRACE? Most people have heard of GRACE. Has anybody not heard of GRACE? A few people have not heard of GRACE. Good. GRACE is brilliant. It's just brilliant. We live in a time of wonders and miracles. Whoever thought that relativity would give us such a fantastic tool? It's two little satellites that go around the Earth and they chase each other. And they measure the relative acceleration, deceleration between them that is related to what's happening on the ground. And this can be groundwater changes. So people have used GRACE to find out that India is depleting its groundwater through irrigation, which is interesting. And we can also use it to measure ice sheets, and we can measure the relative change in the mass of ice sheets. And that's what this shows here. So this is GRACE data from these three periods. So this is the whole period, 2003 to 2012. And what you can see here is we had a massive loss over southeastern Greenland, and this correlates to what I just mentioned. There was a warm ocean current that came up here, entered the fjords, and it triggered a mass retreat. And all these glaciers, outlet glaciers in these fjords, retreated and lost a lot of mass in the early 2000s. And that's basically what we're seeing here. Later on in the sort of early part of this century, saw massive increases in melt also on the west coast, and also retreating glaciers all the way up. So this is what we're seeing here, is in the later part we're seeing both the melt and the dynamic signal in the GRACE data. And this is integrated over the whole of the Greenland ice sheet. This shows that in the early part of the record, we were sort of positive, and then we went negative sort of roughly around about 2006, and now we're getting very negative. And 2012 here, as you probably know, is a very high melt year over the Greenland ice sheet, and we actually see this in the GRACE record. We see years with very dramatic melt in there. So GRACE is fantastic. It's going to go offline quite soon, and there isn't a replacement yet, but they're working on it. So hopefully we get new GRACE. So, as I said, we can more or less divide up mass balance into these different components. And you do get different results for the different components depending on which technique you're using. So this is one of the first attempts to try and reconcile all these different estimates of the mass budget. And they came up there, they're using RACMO, which is a climate model, with INSAR, and they use INSAR as a radar measurement, and it's used to calculate velocity. And they combine these two techniques to measure how fast the glaciers are moving, especially the ones that carve into the ocean. And they come up with a total for the whole ice sheet of minus 260. 250 gigatons per year over the whole ice sheet, which, if there's any oceanographers here, is about 8 millisverdrups. Sverdrup is a funny unit, but oceanographers seem very fond of it. Basically what you can see here is that in the north we have a low negative surface mass balance. This region here includes the northeast Greenland ice stream, which has just had a very interesting paper by Abbas Khan at DTU about these glaciers that have been accelerating and retreating. This area here is largely the Jakobshavn Basin, which is the fastest glacier in the world. I'll come back to that. And you can see this area here, the southeast, is giving us, it's the only area, these two areas here, are the only areas where we have a bigger dynamic component and surface mass balance component. And that's partly because all the snow, much of the snowfall in Greenland falls in this area, but also because of this acceleration and retreat of the outlet glaciers that we saw in the early 2000s. And overall dynamic mass loss is smaller than SMB. We used to think it was about 50% SMB dynamic, and most people now say it's about 1/3 dynamic, 2/3 SMB, but these numbers can vary on quite short timescales, depending on what's going on. So then 2012 happened. Does everybody remember 2012? It was very exciting working here in 2012. We kept getting rung up by journalists. This is melting. By the way, this happened when there were 2 people, and only 2 people in my department at the time. That was me and Jens Hasselberg, and everybody else was on holiday. So that's why it was quite exciting. So we had 3 days where we saw much of the ice sheet melting, and this is from satellite images. And 2 different satellite products, MODIS and this SSMIS. I'm sorry, I made a note to myself, I forgot to delete there. We'll come back to that. And just to show we could model this, we modelled it, and there it is. It's not a perfect match, but this is the sort of the July, the total July, rather than the actual 3 days that I'm showing here. And this event was so significant that it's left its own melt layer. I hope you can see this. This lighter band here is the melt layer from 2012. And this is actually from the Nîmes site rather than from Summit. And this melt event really caused some problems at Nîmes because the planes couldn't take off and it got really slushy and wet and nobody really wanted to do anything. So now we can actually see this in the shallow fern core record, this band, and this has interesting implications for the albedo of the ice sheet, which I might come back to if you're interested. The first question that I was asked when all these journalists were ringing us up was, has this ever happened before? And we had to say, well, no, not in the satellite record, but this handy paper was published in 1994, had actually found similar melt layers at the summit, or actually at GISP2, which is close to the summit, I guess, with these kind of thin ice layers. And many of them sort of correlate to this warm period in the Middle Ages. So it has happened before, it just hasn't happened very recently. So that's, how do we observe surface mass balance? Well, as you've seen, we can send satellites and get a rough estimate. We can look at the melt from satellite sensors. But if we want to know exactly how much is melting or exactly how much is carving off, then we need to run some models. And this is a beautiful project at GEUS, the Geologische Universität. Here, the PROMICE project. Who knows about PROMICE? Does everybody know about PROMICE? Few people know about PROMICE. Okay, PROMICE is really cool. If you're interested in Greenland, then you should definitely look at the PROMICE website, because each of these little yellow dots here are weather stations. And their data is being fed live into a database at this website. You can actually go and click on these little yellow circles and it will tell you what the weather's been doing, how cold it is, how windy it is, air pressure, relative humidity, that kind of thing. And this is one of their sort of standard weather station setups. This is Dirk van Aas, who some people might know here, looking kind of cool in a sort of outdoors model kind of way. Dirk is running basically a model that he's developed based on this point data that generalizes it over a larger area. So that's one way you can do it. The PROMICE records only go back to 2008, unfortunately. Wish they were a bit longer, but it's there and it's still going strong. But what do you do if you don't have any data? Well, you use a model. That's what we're told. So, modelling surface mass balance in a climate model. There actually are a few climate models that do this. One of them is at DMI. I'm running it. And many of these are the kind of things we need to take into account when we want to calculate surface mass balance in a model. Precipitation, we already have that. We need to calculate the melt, and that's this, I'll come back to that. We need to know the ice temperature lower down so that we know the heat flux into the glacier. We need to be able to take into consideration melt and refreezing. So basically, most climate models already produce these kind of things. Radiative fluxes, the sensible heat, the latent heat. So it should be quite straightforward to calculate surface mass balance in a climate model, which is nice. So energy balance modelling. This is very standard in a climate model or a weather model. And we need to modify this so that we can calculate the melt of the glacier surface to get surface mass balance. So, what do we have here? We have net shortwave, and our net shortwave is the downward shortwave radiation from the sun, minus the element that is reflected. And this is why the surface reflectivity of the glacier is really important, and why snowfall is really important. Snowfall is very white, at least in the visible wavelengths, so it reflects a lot of the shortwave radiation. Ice, as you can see on this picture, this is an East Greenland picture, by the way, this is Greenland Glacier. Ice is very dark, it absorbs rather more of the shortwave, and you get much enhanced melting as soon as the glacier surface is exposed. Long wave, much of it comes from clouds, scattering and whatnot, and then we have a long wave flux emitted from the surface, which is the reflection surface temperature largely. Precipitation, very, very important. This is our accumulation term. We have evaporation and sublimation term, which is also important in Greenland, especially in wintertime. And then we have to take into account melt and refreezing, and this is done in the models, and we've just implemented this in our model. Then we need to find out the latent heat flux, which is a reflection of the change in phase at the surface of the glacier, and the sensible heat flux, and melt and runoff. And basically, the energy budget has to balance. The surface of the glacier cannot go above 0 degrees. So we balance this budget, and if this says that we have energy left, this is melt energy, and this is used to calculate melt. I hope that's clear. Does anybody have any questions about this? Good. So this is a slightly simplified version of what we're doing in our climate model at the moment. I'm going to talk about our climate model system, because this is what I do on a day-to-day basis. So I run this model, here HAM5, and I've put in this surface mass balance module so we can calculate directly what the surface mass balance of Greenland is. We can force this model with a global climate model, like EC Earth, which we also run here, or we can force it with a weather forecast model, and your illustrious treasurer, Christian Hay, runs a weather forecast model for us, and I will come back to this later. We can also use reanalysis data sets. Does everybody know what reanalysis is? Does anybody not know what reanalysis is? Reanalysis is basically output from a weather forecast model for a long time. I think that's probably the best way to think of it. And we feed this into the edges of our regional climate model, and it solves lots of equations, and then it gives us output like this. And this is actually just showing precipitation, this particular plot. We also run an ice sheet model, and this is kind of important because this is what gives us our dynamic component of the total mass budget. And this describes how it flows. So we build up lots of snow on the top, and then it flows out to the edges. There are probably only 3 groups in the whole world that run a climate model, a global model, or a regional model directly coupled dynamically to an ice sheet model, and DMI is one of them. So I think that's quite cool. Denmark's kind of leading the world in terms of being able to do this kind of stuff. So it's quite interesting. So some results. So what's the surface mass balance of Greenland from climate models? And this is what made it into the IPCC report. This is only for the Greenland ice sheet, and these are lots of different models. RACMO2 is run by the Dutch, MAR is Belgian, PMM5, this is an American model. This is the reanalysis data set that's driving a rather simpler melt model, and this is a snow model, which I think is being driven by this ECMWF. And then this goes back to 1960. We have only run our model back to 1990, which is why it's not included in this graph here, so I've put it on top. And all of these models show that it's been a fairly, this is just surface mass balance that I'm on the bottom graph. You can see it's pretty noisy. There's quite high interannual variability, And then the last sort of part of this century, it's had a sort of downward trend. We see the same pattern here. Our surface mass balance is slightly higher, and that's because our precipitation is slightly higher than these models. And the reason for that is that this includes all the small glaciers and ice caps around Greenland, which is where most precipitation falls. And these are only the Greenland ice sheet, so they're not quite captured. It's not quite the same thing that I'm showing here, but it's similar. And the main thing to take away from this is that actually we see exactly the same pattern here that we see in these other climate models. And we're mostly, Hirham 5, which is our model, is most similar to RACMO, which is the dark blue line you can see here. And everybody goes off the scale in 2012 because I think this actually only goes to 2011, but this goes all the way to 2012. You can see 2012 is significantly more negative than any other year we've seen. Oh yeah, so this is just to show that it looks like our precipitation is very high when you compare it to other models, but when you compare it to the ice core records, it's actually damn good. So it's just to say that. So why has it been very negative in the last few years? Well, the main reason is probably the North Atlantic Oscillation. Everybody know the North Atlantic Oscillation?
Yes.
Good, good. It's quite basic, this. So we have had some fairly wet summers in Denmark, I think it's fair to say. Maybe not last summer, but the summer before it was quite wet. But it was quite dry and warm and sunny in Greenland, and that's what you can see here. We've had these persistent negative phases, which brings very clear skies, lots of lovely shortwave radiation over the ice sheet, and warm air. And often it's been rather dry, and if I just go back here, you can see that at least part of this declining signal, it's hard to see here, but it is a little bit drier here compared to the sort of average that we have when we go further back in time. So at least some of the sort of dramatic melt events that we've seen in the last few years, and we also had big melt events in 2010, 2009, I think, am I right? 2007 was also quite a big melt event year, and was also a record low for the Arctic sea ice. But as a result of this, the albedo of the ice sheet, this is the albedo over the whole ice sheet, so it includes the high area and the low area, which is much darker than the higher. You see the albedo of the whole ice sheet has actually declined, and this is measured from MODIS satellite, so this is measurement rather than model. And this is probably because we're getting these more intense melts that's going higher up the ice sheet, and that's leaving these these ice layers that I showed in the snowpack, and this absorbs much more than the snow does. So there is a feedback going on. There may also be an influence from black carbon from forest fires. It's very early days to actually be able to say that that is the case, but there is some evidence that these sort of big forest fires they have had in North America and tundra fires are actually wafting over the ice sheet and depositing black carbon on the ice sheet. It's very early stage to be able to say if that's actually what's happening here or not. So, what will happen in the future? This is what everybody asks me. Sometimes in not very polite terms, people say, so what's going to happen? This is also the point in a talk when people show pictures of polar bears. Everybody loves polar bears, don't they? My office mate Martin said, you need more pictures in your talk. So I said, oh, I can't show penguins, it's Greenland. He said, polar bears, people love polar bears. So, gratuitous polar bear shot. This is the best one I could find, sorry, this is in Svalbard. And it's from a distance, I've zoomed in quite a lot. This is a mother and two cubs, they were very cute. So I thought, this isn't really on. So there's another polar bear shot. This is my little 18-month-old daughter seeing her first polar bear up close. It's not alive, obviously. So this was actually in Rikshospital last week. I don't know why they have a polar bear there, but anyway. So what will happen in the future, and our polar bear friends are always very excited to find out. So, future sea level rise. It's quite complicated. I need to ask for a volunteer from the audience at this stage. It's not complicated. Is somebody we're going to visualize some sea level rise from Greenland. Somebody prepared to help me with a ruler and a tape measure? Volunteers? Volunteers? Anybody volunteering? John is being pointed at. The whole reason I'm here today is because John Kaplan said, I need you to write me something about Greenland for Veer. So, yes, of course I can write you something for Greenland.
Der kommer en artikel i næste nummer.
Yeah. So, this is our total sea level rise. And remember, this is a ruler I stole from my children. Can you find 6 millimeters on there? Maybe, just about. Maybe you can hold it up to the audience.
6 millimeters.
6 millimeters. Yeah, so 0.6 millimeters. Very small. You can't really see that. It's pretty small. I've got a long ruler right here. So, this shows A1B was the scenario, the sort of worst case scenario, more or less, in the last IPCC report, the AR4, not the AR5. And it's kind of hard to visualize what that means. So if we take the mean value, this is about 0.5. So if you can unwrap this bigger one, show everybody 0.5.
0.5 what?
Meters.
Meters,
Yes,
yes.
this is in meters. A global mean sea level rise.
This is 0.5.
0.5. Very good. And then we have our RCP 2.6, which remember I said was wildly optimistic, and that's down at about 0.4. So that's 0.4 on top of present day sea level. RCP 4.5, which is the one that everybody's been using to run their models because it looks kind of average. This is actually not much more. It's 0.45 when you look at the numbers. So imagine Copenhagen Harbour with a little bit more water in it. And then RCP 8.5 is about 0.6. So this looks quite reasonable. Everybody's quite happy that we can deal with this kind of 0.4, 0.6. And then we look at, so this is just to the end of the century. So this is 2081 to 2100. So we're just looking at the last 20 years of this century. But this is quite complicated. I'm only really going to look at this graph here. This is how much sea level rise in total, assuming that we reach the end of the century and then emissions don't continue to go up, but we follow these representative pathways, and this is the temperature along the bottom. So this is how much sea level contribution from these different parts of the cryosphere and thermal expansion. How much do we expect? So 1 degree Celsius. Now it's quite difficult to say because there's a very wide spread in the models. But let's say 1 degree Celsius, best case scenario, we're about 0.5, which you've just shown us. 1.5 C, which is about here, the average has suddenly gone up to 6 meters. And to visualize 6 meters, I brought you a tape measure. Oops. So maybe you want to... Unfortunately, I only have a 5 meter tape measure at home. So you have to add your meter to the end. So this is
1 meter here.
So this is about 6 meters sea level, which we've locked into if we allow temperature to get to 3-4 degrees Celsius. But this, I mean, the timing of this is complicated, and as you can see, the model spread is quite high at this point. And 6 meters essentially means that most of the Greenland ice sheet disappears, because the Greenland ice sheet is about 7.3 meters if you...
And most of Denmark too.
Yeah. Well, not if Antarctica stays where it is. I haven't got into the Antarctic figures. I would say that the smoothness of this graph gives away that we don't really understand Antarctica very well. But this is something to consider. Of course, this is going to happen in the far distant future. None of us will be around, and probably our kids won't even be around. But I think it's something interesting to look at. Yes.
Why does it jump like that? It seems like some critical point.
Yes, and all the models seem to show that, and it's just because. So I should say this is globally average temperature, by the way. So we see much higher warming at the Arctic latitudes, and basically Greenland is an artifact. It shouldn't really be there. It's only there because it's already there. So it keeps maintaining itself. The climate of Greenland is very. It's because it's high. Yes.
You are not saying that in the next 100 years Greenland will disappear.
No,
so what is that kind of equilibrium or?
Yeah, it's basically
infinite?
it's an equilibrium at some point. Basically, it's still still not terribly well known how quickly Greenland will disappear, because we don't really have the models that are capable of dealing, especially with the dynamic mass loss component. But yes, at some point it gets to this point, and then this is, well, you can see some of the models have it disappearing much earlier than some of the other models, so there's a really big spread here. But effectively, the height of the ice sheet drops below a critical point, and then it can no longer maintain itself because it's not getting enough precipitation in the wintertime, and the whole thing just goes. But it's, I mean, it should be said, this is 6 meters here. It doesn't quite make, yeah, this is disappearance level, because it's about 7.5 meters in the Greenland ice sheet, but there'll probably still be bits of it in, yeah, eastern Greenland.
But how long will it take?
Yeah, a long time.
Okay.
Yes.
But if we look at the Eemian
Yes.
last warm period, many measurements from Greenland point to the fact that there was actually ice left on Greenland.
Exactly, yeah, and I think this really shows that we really don't understand the ice sheet that well. I mean, this is just the model spread, and this is global temperature, so don't forget global mean temperature. It's not the temperature in Greenland. If it's the globally goes up by 4 degrees, then Greenland is going to be significantly warmer, and probably we don't really have a very good grasp on exactly what will happen.
Do you have a feeling of how long it would take if we reach that level? So this vertical part, how?
I could give you a number, but it wouldn't be based on anything more than
No,
intuition.
would it be 100 years?
No,
or
it would be millennia to get
okay.
to that.
No, but I mean the actual transition,
Oh,
not
the
the not to get there, but the actual transition. Would that be in a lifetime?
I think it's very unlikely. So, don't worry. By then we'll have all moved to places a bit further inland, and probably don't buy anything on the beach. I think that's probably what's said. So I hope I've convinced you that it's kind of important that we try and understand these systems. Has anybody seen the polar portal yet? Some people have seen the polar portal. Some people are running the polar portal. So it's kind of important that we find out what's happening with Greenland, and this is really a nice way of actually being able to see in real time what's happening to the mass balance of Greenland ice sheet. We are fully up to date. We have a Twitter account at Polar Portal, and we have a Facebook page. Feel free to come and like our Facebook page, and we're posting kind of stories and videos and stuff that doesn't go on the main site on the Facebook page. And these have only just been set up, so they don't have very much content on them yet, but we're getting them. There's lots of things on the Polar Portal, so I'm going to talk about a few of them. This is the Heerlam weather model that Christian is running for us on the Polar Portal. And we're using the output from that weather forecast model to force the surface mass balance scheme of Heerlam. So it's not actually coming from Heerlam, but it's the same surface mass balance scheme we use in Heerlam. And every day we update it, once a day, and you can see what's happening right now over the Greenland ice sheet. So this shows that, I mean, it's pretty boring at this time of year, I have to say. Not very much happens in Greenland at this time of year. We get a little bit of precipitation. Sometimes we see a little bit of pink appearing, which is usually a sign of sublimation or maybe a bit of melt. It's been pretty cold in Greenland lately, so we haven't seen very much of that. This shows the sort of weather events, basically. So you can see we've had some fairly big snowfall events. And this is the accumulated mass balance over the course of the hydrological year. And I should say that this goes from September to September, because that's how sort of surface mass balance season. We have this long, slow increase in mass from snowfall, and then it starts to melt and run off, and we have this fairly rapid decline, and then it starts to go up again. So we trace it from September to the end of August, basically. The grey box here is actually the results of 20 years worth of Heerlam simulation. So it's the same surface mass balance model, but it's a slightly different forcing model. And we've plotted for interest, we've plotted the 2012 melt season, which had this very deep dip. And sorry, this is 2011 to 2012, and then this is 2012 to 2013. And this counted as a fairly average year by recent standards, but it was still very much on the low end of the sort of the Heerlam simulated 20-year simulation. And you can see, so every day this line gets a bit longer and and this line gets a bit longer, and then eventually we come up with a total number at the end of the melt season. Oh yes, as I mentioned, can you see this? We simulated 2012 with this system, and we got quite dramatic results. And just to show that it really did happen, it wasn't just in the models. This is the temperature record from Summit in Greenland, and these are the days when the whole ice sheet was melting up here. And you can see actually this temperature record is quite interesting. It shows that it's actually not unknown that you get temperatures above 0 degrees at Summit. This one is a bit funny. This is the highest recorded temperature. Do you know, John, is this considered real? Because
I haven't removed it.
you've removed it from the record now, because when you look on the temperatures either side, it's well below 0. So I was looking at it thinking, I'm not sure I believe that. But this was certainly true, and we have backup data from other weather stations.
There are several stations on Summit, so we can compare them.
Right.
So it's not true.
Okay. Good. I got this one off the homepage rather than from the data set. So this is one of the nice things on the Polar Portal, you can see. This is also, by the way, on the DMI homepage. And then you can also look at the dynamic mass budget. We have glaciers all around Greenland that are being monitored, and whenever there's a nice, clear new satellite picture,